Thank you so much. So yes, my name is Serena, and I'm a PhD student at the Max Planck Institute in Hanover. And today I'm going to talk about a project that, as the title says, focuses on testing the strengths, the limitations, and the possible biases in the detection analysis pipelines that are used in pulsar timing arrays and analysis. So before going into the details of this project, I want to give a little bit of background about what is a pulsar timing array experiment and what's the main idea behind it. So the idea is that we have our pulsars, which are very stable, fast-rotating neutron stars, and those objects are so stable and so well known that we can actually predict with very high accuracy the time of arrival of those pulses. We can build a timing model for each pulsar and predict all those time of arrivals. So we do that, we build all our timing models, and we compare the predicted TOAs with the ones we actually observe. And what do we notice? We notice that they agree quite well, but there is some kind of differences between what we predict and what we actually observe. There are some residuals. So there is some effect that we haven't modeled in our timing models. And what is this effect? So the pulses are propagating into a gravitational field. So there are gravitational waves that are accelerating or delaying the propagation of those pulses. And so we can actually look into those delays and use them to infer some information about the gravitational waves that are modifying the path of those pulses. What is the gravitational wave signal that we're interested in? So with PTA experiments, we are sensitive to frequencies that goes between nanohertz and hundreds of nanohertz. So the main expected gravitational wave source is the superposition of emissions from supermassive black hole binaries. So we have all those supermassive black hole binaries which are emitting monochromatically. And what you can see is just a superposition of all those signals that creates what's called a gravitational wave background. So in this project, what we did was actually to focus on the sources of this gravitational wave background. And in particular, we took the model for those sources and we tried to relax some of the mainly used assumptions and build more realistic models and see if we were still able to correctly, in a robust way, recover the signal that we were injecting. So how do we do that? What is the main assumption that we use when we build a gravitational wave background? So we consider our sources to be astrophysical supermassive black hole binaries. We assume all of them to be circular and fully gravitational wave driven. It means that for now we are ignoring all possible environmental effects like gas hardening or stellar hardening, but we are considering a pure gravitational wave emission. And those binaries are producing a signal which is modeled as a common red noise common through all the pulsars and especially correlated following the Ellings and Downs correlation. And we assume also the signal to be stationary, isotropic, and with a spectrum which is a smooth power law with some Gaussian variations around it. But this is the ideal model. This is the ideal model that we use, that it's encoded in our enterprise recovery pipelines, and this is the good model that describes on average what we are looking at. But the point is that in reality we are not looking at an average, but we're looking at a specific realization. So we try to relax some of those assumptions, and in particular, we want to get rid of the assumption that the background is isotropic and has a spectrum which is just a smooth power law with some Gaussian variations. How do we do that? So from simulations of galaxies evolution and supermassive black hole binaries formation, we can actually write a catalog of a possible realization of the universe, of a possible population of supermassive black hole binaries that we can have. We can actually infer some information about their masses distribution, their redshift distribution, the frequency of emission. And we can write a catalog of supermassive black hole binaries, a possible one, and compute the gravitational wave signal produced by each of those binaries and build a spectrum. And what you think, for example, in one realization is this brown line. So this brown line, as you can see, it's well fitted by the power law, especially in the lowest frequency fields, which are the ones our PTA experiments are most sensitive to, but has a much more structured profile. So, and this is one realization. Can we derive a different one? Of course, we're deriving all those information from different probability distribution. So we can derive different realizations of a background which is always meant to produce a very similar background with the same nominal amplitude and slope. But if we look at the individual realization, we see that some of them have a much more structured profile with maybe some bright peaks or some dips into it. So how well does our model on average recover the background if a realistic one can be much more structured than what we predict? So we need some statistic to do this kind of analysis. What have we done? We have written this catalog of supermassive black hole binaries 100 times. So 100 different realizations of possible supermassive black hole binaries population that we have in our universe. And for each of them, we have computed their derived gravitational wave background and created a simulated data set that was aiming to reproduce the latest PTA data release. So we were simulating very comparable levels of intrinsic noise for all the pulsars, similar cadences, and all like this. And we did 100 realizations of those realistic populations, so with the supermassive black hole catalogs, and another set of 100 realizations where instead we were just modeling a Gaussian isotopic background. We performed our analysis with the search for the GWB, and we compared the results. So from now on, there will be two sets of data in each plot, a green one, which is the ideal Gaussian isotopic one, and orange one, which is the simulated one from catalogs of supermassive black hole binaries. So if we build our data sets and we perform the search for the amplitude and the slope of the GWB, what we get are those posteriors. Those are the average of all the posteriors that we got for all the 100 realizations. The vertical line is the nominal injected amplitude and slope that we use for our realizations. And as you can see, the green posteriors, which are the ones for the ideal Gaussian isotropic data sets, are much more consistent with the injected value with respect to the orange ones. The orange one seems, on average, to be biased towards the background, which has a much lower amplitude and a higher gamma. What does it mean? It means that, on average, our pipelines on this realistic data set seems to recover a spectrum which is a bit steeper and with a lower, with a lower amplitude than with the nominal one we actually injected in. So, to look again at this bias from a different point of view, we did another statistical test, which is the PP plot. And I don't need to give a big introduction to this because Pep just described what the PP plot is. So just to keep in mind how to read a PP plot, the PP plot is just used to compare the results and compare that the model you use in the recovery of your parameters is consistent with the one is actually used when producing the data set. So there is no inconsistency between the injection and the recovery. Thanks. And so how to read a PP plot? If your data distribution follows along the diagonal, it means that your recovery is unbiased. If it's above the diagonal, it means that your recovery seems to be biased towards a recovery of a higher value with respect to the nominal injected one. Below the diagonal means on average you recover a value which is lower than the nominal injected one. So we built the PP plot for both the green ideal dataset and the orange realistic one for the amplitude of the GWB. And as you can see here, we are clearly always below the diagonal. So for the green dataset, which is the ideal one, we are much closer to the diagonal, and it can be that with a higher statistic, so maybe with more than 100 realizations, we'll get much closer to the diagonal. But the orange one, the realistic one that was built from an actual catalog of supermassive black hole binaries, you can see that there is a clear indication of a possible bias towards a recovery of the amplitude that is lower with respect to the nominally injected one. So this was the recovery on average. So we built some data sets, we did some statistics, and we studied on average how robust is our recovery. But as I said, we looked at into individual realizations of the universe. And also what we are looking at in real data is not an average, but it's a specific realization of the universe. So it's very interesting to look at some of those individual realizations, some what we called in the paper some notable realizations, and see if there are specific features who are creating some funny results that it's interesting to look into in details. So now I want to show one of those notable realizations, actually two because I need to do a comparison, and I chose those two. As you can see, those are two realizations that still are fitted by the nominal power law, but they present this bright peak. This bright peak corresponds just to a very bright source which is quite close by and produces this peak in the spectrum. So what did we do? We built our data sets for both catalogs of supermassive black hole, and we performed the search for the amplitude and the slope of the GWB. So now, if we look only at the first 4 lowest frequency beams, we see that in the recovery of the GWB parameters, there is no actual difference between the two realizations. They are very consistent, and also the posterior are very consistent with the injected nominal values. So if we look only at the lowest frequency beams, everything seems to work perfectly. There is no apparent mismatch between our model and the actual data set that we are looking at. But what happens if we look at a wider range of frequency? What happens if we include also the frequency beams that have these bright peaks? Then the posteriors definitely move away from the injected value. And you can see that the two peaks don't seem to be that different, but the difference in the posteriors is very high, especially the red posteriors get much far away from the injected nominal value. But still, if we look at the whole spectrum, we fit the whole spectrum, the best fit is still the power law that we have. But the point is that in our PTA datasets, we cannot look at all the frequency bins. We have some, we have some sensitivity only on the lowest, like 9, 10 frequency bins. So this is an example of how the presence of the bright source, if not modeled properly, can actually introduce some bias in the recovery of the spectrum. So to conclude, I just wanted to show this plot on the left. It shows all the 100 realizations that we produced of those supermassive black hole binary catalogs. And the bold black line is actually the average between all those spectrum. And you can see that on average, our model very well describes our spectrum and our possible datasets. But we always need to keep in mind that the universe we are looking at is not an average, it's a particular realization. And because of that, it may have some particular features that, if not modeled in the proper way, may introduce some biases in the recovery or may lead us towards misleading results. So yeah, that's all. Thank you very much.
Thank you, Serena. Questions? Oh.
Is that bigger to 1 year?
Yeah, it's a PTA simulated dataset with, the elite Tempo enterprise tools that just create the Gaussian isotropic background. Yeah. So as I said, it may be just some statistical effects on poor statistics. We did only 100 realization. It may be that with a higher number of realizations we get much closer to the diagonal, but still it's quite consistent within one sigma from the amplitude. Plus those are searches which have like a lot of free parameters also that are varying. So it's a quite good result on average for the HWBs. We saw that, for example, if we don't include all the sub noises, etc., the recovery for the amplitude of the HWB is basically perfect with HWB.
Any other questions? Yep.
So there are two things involved, both observations of galaxies and how they form, and there are different models about the distribution of masses from galaxy observations, and you can infer the population of supermassive black holes. There are different strategies. You can choose different models. You can decide to infer them by looking at the relation between the mass of the black hole at the center of the galaxy and the mass of the galaxy itself, or a mass of the black hole and the velocity dispersion of the galaxies. And there are all those astrophysical models about galaxy clustering and transformation that they describe actually statistical distribution, and you can do numerical simulation to draw realizations on those. So it's a combination between observation of galaxies and their formation and also the star formation, and actually the numerical simulations drawn from statistical distributions. So there is this paper from 2013. Serena 2013 is the paper we used to build the models. They actually compare different methods to build the populations using different distribution, for example, for the mass of the black holes and for their redshift distribution. And we took one of those models that was described in that paper, and we used that to draw realizations of the black holes.
Okay, there's a question there.
So what has been done sometimes is that instead of fitting just for a power law, you fit for the amplitude and the slope, you can do what we call a free spectrum analysis. So in each frequency being, you fit for the spectrum individually, but it's much more computationally expensive. And still you don't get super constrained posteriors. But it's what we do that on real data also. We do also the free spectrum analysis, and there are those violin plots that you see in all the data releases. They're all those violin plots, and they are well fitted by the power law.
That's all the time we have for questions. Thank you.